everyone, my name is Amma. I will be introducing you to gravimetric analysis. Gravimetric analysis is one of the most accurate quantitative analytic techniques used in chemistry. It determines the amount of an analyte by converting it into a pure, stable compound of known composition, which can be separated and weighed. Since the analysis is based on direct mass measurement, gravimetric analysis provides high accuracy and precision. One important application of gravimetric analysis is the determination of calcium. Calcium is an essential mineral required for strong bones and teeth, muscle contraction, nerve transmission, and many biological processes. Therefore, determining the calcium content is important in food analysis, dairy products, nutritional supplements, and pharmaceutical manufacturing to ensure product quality and accurate nutritional labeling. The objective of this experiment is to determine the amount of calcium by converting calcium ions into an insoluble precipitate of calcium oxalate monohydrate and calculating the calcium content from the mass of precipitate obtained.
For the theory of gravimetric analysis, the principle of this experiment is based on precipitation gravimetry. In this method, calcium ions react with oxalate ions supplied by ammonium oxalate solution to form an insoluble white precipitate known as calcium oxalate monohydrate. The chemical reaction is shown below. Ca2 plus will react with C2O4 2 minus with water will form CaC2O4 H2O in the form of solid. Since calcium oxalate monohydrate has a fixed chemical composition, the amount of calcium present in the original sample can be accurately determined from the measured mass of the precipitate. To obtain the reliable results, the precipitate must be completely formed, carefully filtered, thoroughly washed to remove impurities, dried to a constant mass and weighed using an analytical balance. Any loss of precipitate or contamination during these steps may reduce the accuracy of the analysis. Next, I will explain the methodology we used in this experiment. First, we weighed 1.2 to 1.5 gram of onion, and then we transferred the onion to a 250 ml beaker. We then measured 30 ml of the ionized water. We then measured 12 ml of 3 molar hydrochloric acid. Both solutions were added into the beaker containing the onion sample, and the mixture was stirred with a glass rod for several minutes until the material dissolved completely. The clear solution was then transferred into a 100 ml volumetric flask. The beaker was washed 3 times with the ionized water and the washing were added to the flask. Finally, we filled the volumetric flask with the ionized water until it reached the calibrated mark. After mixing the solution thoroughly, we used a small portion to rinse the 25 ml pipette. We then pipette 25 ml of the onion solution and transfer it into each of three 250 to 400 ml beaker. Next, we measure 75 ml of 0.1 molar HCl and added it to each beaker, followed by 5 drops of material indicator solution. We then measured 25 ml of ammonium oxalate solution and added it slowly while stirring with a glass rod. Each sample was added with 15 grams of solid urea. Each wash glass and filter paper was weighed and the mass recorded. The beaker were covered with washed glasses and boiled for 30 minutes until the indicator turned yellow. Each hot solution was filtered through a pre-weighed funnel using suction. We then added 3 ml of ice-cold water to the beaker and transferred the remaining solid to the funnel. Each beaker was rinsed twice with 10 ml of ice-cold water to ensure complete transfer. Using a rubber policeman, we transferred the remaining solid onto the wash glass. Finally, the precipitate was dried in an oven at 105 Celsius for 24 hours. After 24 hours, each precipitate was weighed and the mass recorded for the analysis.
Here we have the data of analysis. We have three beakers, beaker 1, 2, and 3, which is recorded for the mass of filter paper in grams, the mass of glass plate in grams, and the total mass in grams. For beaker 1, the mass of filter paper is 0.34 grams, mass of glass plate is 32.36 grams, and the total mass is 0.46 grams. In beaker 2, the mass of filter paper is 0.33 grams, the mass of glass plate is 31.68 grams, and the total mass is 0.51 grams. For beaker 3, the mass of filter paper is 0.33 grams, The mass of glass plate is 42.63 grams and the total mass is 0.52 grams. We then have the stoichiometry equation, which is Ca2 plus in aqueous plus with C2O4 2 minus in aqueous plus with H2O in liquid, which then goes to CaC2O4 with H2O in solid, or otherwise called as calcium oxalate monohydrate. Then we have the calculation of the mass of calcium. The formula for this calculation is gravimetric factor is equal to molar mass of calcium divided by the molar mass of calcium oxalate monohydrate, which is 40.1 gram per mole divided by 146.1 grams per mole, that equals to 0.2745. Then we have the volume of calibrated value from pipette, which is 25 milliliter, and the volume of calibrated value from volumetric flask, which is 100 milliliter, and we put those two values together and we divide. We get 25 divided by 100, which is equal to 0.25 milliliter. Then we can calculate the mass of unknown solid in aqueous, which is equal to 1.4 times 0.25 milliliter, and we would get 0.35 grams. Next, we could calculate the weight percentage of calcium. In beaker 1, mass of calcium is equal to 0.46 times 0.2745, which is equal to 0.1263 grams. The percentage of calcium in beaker 1 is calculated with 0.1263 divided by 0.35 times 100, and we get 36.09%. In beaker 2, the mass of calcium is equal to 0.51 times with 0.2745, which equals to 0.1400 grams. The percentage of calcium inside beaker 2 is calculated with 0.1400 divided by 0.35 times with 100, which in turn we will get 40% in beaker 2. For beaker 3, the mass of calcium is 0.52 grams times with 0.2745. We get 0.1427 grams, and we can calculate the percentage of calcium, which is 0.1427 divided by 0.35 times 100, and we will get 40.77%. We then could calculate the mean, standard deviation, and relative standard deviation. To calculate the mean, we have to put together 36.09 plus 40 plus 40.77 and divide it by 3. We would get 38.95% as our mean. For the standard deviation, the calculation goes as square root of 36.09 minus 38.95 squared plus with 40 minus 38.95 squared and plus with 40.77 minus with 38.98 squared divided by 3. We would in turn get 2.0489 as our standard deviation. For our relative standard deviation, it is calculated with standard deviation divided by the mean. So we should put 2.0489 over 38.95 times with 100, and we would get 5.26% as our relative standard deviation.
So let's discuss. Adding the relative standard deviation, RSD, obtained in this experiment was 6.44% based on a mean calcium weight percent of 38.95% and a standard deviation of 2.51. RSD is a measure of precision, indicating how close repeated measurements are to each other relative to the mean value. An RSD of 6.44% suggests that precision of the experiment is moderate but not high. In gravimetric analysis, which is generally considered a highly precise analytical method, an RSD value below 2 to 3% is typically expected under ideal conditions. Therefore,
The obtained RSD indicates noticeable variability among the three trials. The variability is evident from the individual calcium weight percentage, like 36.09%, 40%, and 40.77%, but the first trial is significantly lower than the second and third. This deviation strongly influences the standard deviation and increases the RSD value. The lower result in trial 1 may be due to experimental errors such as loss of precipitate during filtration or transfer, incomplete precipitation, or insufficient drying of calcium oxalate monohydrate, which would reduce the measured mass of precipitate. Despite the higher than ideal RSD, the second and third trial shows good agreement with each other, suggesting that the experimental techniques improve or stabilize after the first run. This indicates that the method itself is reliable, but better control of experimental conditions is required to improve precision. In conclusion, the RSD of 6.44% indicates acceptable but limited precision for this experiment. With improved handling, more careful drying, and minimized loss of precipitate, the relative standard deviation could be reduced in future analysis, enhancing the reliability of the gravimetric determination of calcium.
Next is the applications in gravimetric analysis. So there are a few applications in gravimetric analysis. One of the application is in the food industry. So for the food industry, gravimetric analysis is used for calcium analysis in milk and dairy products, and also in nutritional labeling verification. In addition, gravimetric analysis is used in pharmaceutical industry. For example, it is used in calcium determination in supplements plus product quality assurance. And lastly, quality control. So gravimetric analysis is used for accurate and precise calcium measurement, also in compliance with industry standards and also laboratory and research
In
applications.
conclusion, this experiment successfully determined calcium ion by the gravimetric method using calcium oxalate monohydrate as the precipitate. The control precipitation produced suitable crystal for filtration and measurement. The precipitate masses obtained were 0.46 gram, 0.51 gram, and 0.52 gram, showing acceptable repeatability despite slight variation due to experimental errors. Overall, the gravimetric method was effective and reliable for the quantitative determination of calcium.